Hi, welcome to Primal and Dual problem for SVM. Here, as we discussed in the previous video, solving the primal problem is somewhat difficult than solving dual problem. So, if the problem is given in the primal format, then we will convert that into the dual problem. Then we can apply the equations using the KKT and Lagrange theorem to find out the better optimization function for SVM. So here uh, we are going to minimize the given optimization function f of w with respect to the parameter w subject to two constraints. One is gi of w which is less than or equal to 0. So I is having the range from 1 to k. So here this is inequality constraint, and next one is the hi of 0, hi of w equal to 0. So this is equality constraint. To solve the inequality constraints, we can use kkt. To solve the equality constraints, we can go with Lagrange multiplier, right? So now we will write the generalized Lagrange equation with respect to uh, w is the parameter given in the optimization function, alpha is Lagrange multiplier for the equality constraint, and here we are using for inequality constraints, and beta is using for equality constraints here. So when you are writing the equations from the samples from 1 to k range, alpha is the parameter for inequality constraints gi of w, and plus I equal to 1 to l, the range of samples from equality constraints. Here the parameter for the equality constraints and equality constraint function. Now we will define the optimization function with respect to the parameter w as a primal problem. So now we are trying to maximize the value of Lagrange equation with respect to W, alpha and beta. So here alpha should be always greater than or equal to 0. Then we can write this equation from the Lagrange equation, optimization function plus inequality constraint and multiplied with parameter, and equality constraints multiplied with parameter. So this is substituted in this equation, and here we are having the different constraints. So first constraint is gi of w greater than 0. When our gi of w, this value is greater than 0, right, it will not satisfy this condition, because here given condition is gi of w less than or equal to 0. If we get greater than 0, then it violates the constraint. So the term alpha I gi of w becomes alpha for large alpha I. So here always, as per this condition, gi of w always less than 0, less than or equal to 0. So it will be minimum value. So when your this entire value is getting large, so when you are increasing the alpha, automatically you will get the maximized value. So here this alpha is determining your maximizing the value of theta. That is the meaning here. And second constraint, hi of w equal to 0. if we getting if we get not equal to 0, then hi of w not equal to 0, then it is violating the given constraint condition. So here also, when we are increasing the value in negative way for the beta, and hi of w also negative, right? So you will keep on increasing the negative way both bi and hi in this constraint. You will get positive values. So but it should be equal to 0, it should be equal to 0. So this is violating the condition. So here also, when you are keep on increasing that values, you will get positive values, so it is violating the condition, so it should be avoided. Here also this term will get into the picture, so this will decide the optimization function value theta p of w. And when you are increasing the beta value in the positive manner also, it will keep on increase, this term will keep on increase, but it should be equal to 0. So here also alpha will influence the given function theta. Third condition is gi of w less than or equal to 0, less than or equal to 0, then hi of w equal to 0, hi of w equal to 0. So when this condition is considered, it will satisfy the constraints. So now this is the Lagrange function we are having. Then we can say this theta Lagrange function is satisfied the objective function when the constraints are satisfied. If constraints are not satisfied, violate the constraints, then alpha is influencing the function. Alpha is influencing the function. That's what given here, right? When constraints are satisfied, you will get the optimization function will be solved. But if you are violating the constraints, the alpha value will be influencing the theta function. So this can be represented with respect to minimal problem, minimization problem, right? So primal problem is representing the minimization of the optimization function given theta of w. So here we will take the primal problem as min max problem. So minimizing the optimization function with respect to w, and maximizing the Lagrangian function with respect to alpha comma beta, here alpha greater than or equal to 0. The dual problem can be written as max min problem, because primal problem is minimization problem, dual problem is maximization problem. So it should be written as min max function, and dual problem will be written as max min problem. So first we are finding the minimum value from the Lagrangian function, and we are trying to maximize that lower bound value with respect to given parameters alpha and beta. So that is the given here. So minimum problem already we got from the this equation here, this one. So we are trying to maximize that value, right, with respect to dual problem. So maximizing the dual problem, maximizing that with respect to alpha comma beta. So for example, a max min of f of x less than or equal to min max of f of x. So here uh, first we are finding the maximum value, trying to minimize that maximum value. Here first we are finding the minimum value, trying to maximize. For example, when you are taking the f of x is sine of x plus y, then whatever value you are substituting for the minimum y value, right? So here we are taking this terminology minimum y value. So mostly whatever minimum value you are substituting, you will get sine of whatever minimum value, you will get the -1. So maximum of -1 with respect to x, and like that here whatever value you are substituting for the x greater value, you will get maximum value will be 1 for the sine of maximum value. So here maximizing this, whatever you are trying to maximizing with, so this is constant, then that will be a -1. Here also maximum, it is the constant, so it will be a 1. So it is satisfying the condition -1 less than or equal to 1. So from this we can say dual problem less than or equal to primal problem. So we can derive the primal problem from the dual problem. So both will give you the same result, but under some conditions like convex problem. So here the dual problem is convex problem, which is using a Lagrange multipliers. So based upon the conditions like convex conditions, the dual problem always less than or equal to primal problem solution. So first one is when we are taking in these two conditions, when we are taking less d equal to b under existing w parameters w less than beta. So here the w will be the solution to primal, because primal problem will be the minimization problem. So here it will have minimum value, w star give you the solution to the primal problem. But alpha comma beta, so alpha comma beta are trying to maximize the problem, so which will give you the solution for dual problem. And second condition, primal problem equal to dual problem. So dual problem can be assigned to the solution to the assigned to the primal problem. So here we have to satisfy the conditions all three by applying the KKT constraints. First one, we will apply the partial derivative to all the constraints and optimization function with respect to alpha, w, beta, and equate to the 0. So like dou Lagrangian function of dou x1 equal to 0, dou less than w equal to 0, dou Lagrangian function dou beta equal to 0, like that we have to equal to 0. Then constraint alpha into constraint equal to 0, then inequality constraints less than or equal to 0, and fourth condition is alpha always greater than or equal to 0. So based upon that, the dual problem can be assigned solution assigned to the primal problem. So why do we need this primal and dual problem conversion? So here, when we are having the higher dimension data, we will use the kernel function uh, to solve the given SVM problem by maximizing the margins. So here the dual problem is very easy to solve the given problem. So that's why whenever you are getting the problem in the primal, so we can convert that into dual format, then we can solve that easily. So here, even if your data is having higher dimension like 1000 features or 10,000 features, you can use the dual problem by applying the kernel trick, right? So it will give you the solution with less time complexity. Thanks for watching.